Hi, welcome back. In this lecture I want to talk about entanglement, entangled states, non-cloning theorem, and control gates, way beyond control X operation that we defined in the previous lecture. So let's start first defining what is an entangled state and what is a product state. To define when a quantum system is entangled, we first need to explain what is not entangled, and which is called the product state. A state psi is a product state if it can be written as the tensor product of two other states, psi1 and psi2. So generic quantum state psi, as here on this slide, that can be written as a tensor product of two quantum state, then is a product state. What is not a product state is called entangled state. An entangled state is something that cannot be written as a tensor product of two quantum systems. Let's see an example of a product state. Well, the very simple case is the state 01 that is part of our computational basis in a 2-qubit system. And if you remember how we derived that, we took by definition the tensor product of state 0 and state 1. Because by definition this is a state that is derived by taking tensor product, then 0, 1 is a product state. Another example here is the following here. If we have 1 over square root of 2 of state 0, 0 plus 1, 0, this can be written as a tensor product on this slide. The most important entangled state is the so-called Bell's pair that can be found using the Bell's pair quantum circuit that is as follows. So this is defined as square root of 1 over 2 of the state 0, 0 and the state 1, 1. It turns out that it is impossible to write as a product of a 2, 1 qubit state. Let's look at a very simple proof. So if this state can be written as a tensor product of a 2 quantum state, then we can write the following. There must exist A, B, C, and D, such that A multiplied by state 0, B state 1. We take this expression and we multiply by C state 0, D state 1, and D state 1. If we perform this multiplication, then we found this case. So the only state that are different from 0 are this one. Right, so AC must be different from 0, and the same way BD must be different from 0. On the other hand, we do not have this state 0, 1 and 1, 0 here. And therefore, these two guys here must be equal to 0. AD must be equal to 0, and BC must be equal to 0. So we see that this force A multiplied by D to be equal to 0 because we have no 0, 1 component. Then either A is equal to 0, in which case AC is 0, or D is equal to 0, from which results that BD equal to 0. But this is not possible, right? Because this BD must be different from 0. So in both cases, reaching this equality is impossible. And therefore, there is no way we can actually write this quantum state as a tensor product of two simpler quantum states. And therefore, the state is entangled. The entanglement has some physics implication when we measure. Entangled state can show correlation that go beyond what can be explained with the classical physics. What does it mean? Well, let's take an example of the entangled Bell's pair quantum state is the following. Let's say that we measure the first qubit, right? And either we can measure 0 or 1. But we know already that if we measure the state 0 in the first qubit, automatically the second one must be 0. It's almost like the information propagate, instantaneously, right? So we know automatically what is the second one. If we measure the first qubit 1, it means that we are in this state here, and therefore the state of the second qubit must be 1. This means that if we measure the second qubit afterwards, the result will be always determined by the value obtained when measuring the first qubit. It will be the same. I'm going now to talk about the non-cloning theorem, and this is another peculiar property of quantum systems. which they don't allow us to copy information. So let's look at a very simple proof. We would like a 2-qubit quantum gate U to copy the first qubit into the second. That is, for any given quantum state psi, we would need a quantum gate U that takes the values from the first qubit and copy in the second qubit. So see, if this is the generic state, this will result on these quantum gates copy in the values of the first qubit in the second one. So this will also copy the first one in the second qubit. So the results will be psi. If this exists, and if you apply this U gate that is capable of copying to this separable state or product state, we apply the linearity operation. So we bring here inside parentheses and we apply to this state. So U to 0, 0. So this our copy operator to 0, 0 and to 1, 0. So this will copy here our state 0. So will remain the same. And this will copy the state 1 here. So we'll make 1, 1. So this will be, the resulting will be 0, 0 and 1, 1. And this is our Bell's pair. You remember from the previous slide. However, we started from a product state and we then ended up in entangled state, which is a contradiction. So this contradiction implies that no such a copy U gate exists. Notice that this theorem does not imply that we cannot copy classical information. For instance, if psi is 0 or 1, we can easily achieve this copy operation by taking U to be the C0 gate. In general, this theorem applies to unknown state psi. If we know what the psi is, for instance, if we know a circuit that prepares psi starting from a classical state 0, then of course we can create as many independent copies as we want. The non-cloning theorem has a very important role in security and quantum cryptography and is at the fundamentals of quantum key distribution or QKD protocols such as BB84 by Bennett and Brassard developed in 1984. You can find here the paper on the Canvas page, also the paper itself. I will finish up this lecture by talking about the generalization of the control gates. In the previous lecture, we look at the control X or control naught. We can generalize it to any single quantum gate. So for instance, we can have also control Y, control Z, or control Hadamard gates. For any quantum gate, it's possible to define a control U operation, and it's quite easy to do it. So if we have our control on the first qubit here, and then we have the target on the second qubit, that means that we apply the U gate only when the control gate is equal to 1. And what is the U gate? Well, it can be expressed as a matrix multiplication, matrix formulation whose values are defined as follows. So this is just a generalization. It's also possible to construct any control gate provided our quantum computer already implements rotation gates and 2-qubit CNO gates. It can be proved that any 1-qubit quantum gate U can be written as follows. We apply rotation, then A naught B naught C for some angle theta, and gates A, B, and C such that multiply by themselves the results in identity matrix. So if we find these three matrices, an angle theta will exist, and we can formulate this quantum gate U. This can be generalized to control operations, so the X gate becomes a control X gate, and we can write any control U quantum operation in such a way by applying this sequence of operation. This is the last slides. I just want to mention that a control Z gate can be obtained from a control X and 2 Hadamard gates, as shown in the identity of the following sequences. So remember, even if a control version of quantum gates that we want to perform on our quantum computer, but it doesn't exist, we can find equivalent formulation using equivalent quantum circuits. This is the last slide of this lecture, and talk to you soon.